Hi everybody, welcome back. In this video we're going to start our examination of spectra and how we can use stellar spectra to learn about stars. In particular, in the video today we're going to discuss blackbody radiation and answer the essential question: how do astronomers determine the temperatures of stars? So here's a nice picture of the famous Horsehead Nebula. And there are a number of features in this picture that we're going to be examining in more detail in the next couple of videos. And similarly in this picture of a young stellar cluster. Now this is what we call a continuous spectrum. Blackbody radiation is something that comes from any object that is essentially warm and is a reasonably perfect absorber of radiation and a reasonably perfect emitter of radiation. And when you have a blackbody, you're going to get what we call a continuous spectrum from it. This is the continuous spectrum of something emitting blackbody radiation, mostly in the visible part of the spectrum. So, as we mentioned, a perfect blackbody is a perfect absorber and a perfect emitter. And a result of this is that it's in thermal equilibrium with its surroundings, meaning that it has the same temperature, and it accepts any photons incident upon it and emits them perfectly as radiation to remain at that same temperature. Now, we'll notice a couple of features of blackbody spectrum. This is a plot of flux, that is basically luminosity per distance, in this case also per unit wavelength, but a plot of flux versus wavelength for blackbodies of a number of different temperatures. But the blackbodies all have the same surface area, and they're just warmed up to different temperatures. The point about them having the same surface area is important because you need to compare objects of the same surface temperature in order to understand similarities and differences in the blackbody spectrum itself. So what we notice is a couple of things. First, as we increase the temperature, the spectrum becomes stronger at all wavelengths. In other words, the object emits more energy at all wavelengths, not just at wavelengths around its temperature, but at all wavelengths as you increase the temperature. Second, as you increase the temperature, the peak of the spectrum occurs at shorter wavelengths. And if you think about it, this can kind of make sense. Remember that the shorter the wavelength, the higher the frequency, and thus the higher the energy of the photons being emitted. So when you have an object at a higher temperature, it becomes more efficient to emit more of the energy at these shorter wavelengths. So those are the two big features of blackbody spectra. For an object, as you heat it up, it emits more energy at all wavelengths, and as you heat it up, the peak wavelength occurs at a shorter, the peak flux occurs at shorter and shorter wavelengths. So that's something that you absolutely must remember about the blackbody spectrum. Now, what about the total energy that the object emits? So that total energy can be found by taking the area under that curve and using some calculus. And after that's done, we realize that the total energy that the object emits, first of all, is going to be proportional to the object's area. The bigger the area, the more energy it's emitting. Second of all, it turns out that the total energy, that luminosity, the power, is proportional to temperature to the fourth power. So if you double the temperature, the object's going to emit 16 times as much power. Third, there is a proportionality constant that comes out of that in addition to the surface area of the object. That's something called the Stefan-Boltzmann constant, which you don't need to know, but I just put it up here so that you all understand that, hey, this actually is a true mathematical formula that's found by taking the area under that curve. So, main points, proportional to area, surface area that is. In this case, if it's a sphere, 4 pi r squared. Second of all, proportional to temperature to the fourth power. So some examples. Let's calculate the luminosity of our sun. How about that of Betelgeuse, and then R136A1. So, first of all, with our sun, which has a radius of 6.955 times 10 to the 8 meters, and a surface temperature of 5,777 kelvins, well, just plug the numbers into the equation. We have the temperature, the radius, plug it into the formula, and when you do that, you end up getting a luminosity of 3.8 times 10 to the 26th watts. That's a lot of watts, and it's also a number that we've come across before when we were just giving some examples. What about Betelgeuse, which has something like 1160 solar radii and a temperature of, what, 3600 kelvins, was that right? Yeah, 3500 kelvins. So, in the case of Betelgeuse, well, in this case, we're given the radius in terms of the sun's radius. So what we can do is we can set up a ratio, basically do a trick, and realize that, okay, if luminosity is equal to 4 pi r squared sigma t to the fourth, then the ratio of the luminosities of two different objects is going to be given by the ratio of their radii squared times the ratio of their temperatures to the fourth power, because after all, the 4 pi's go away, as you can see, when we take the ratio. So, since r is given in terms of solar radii, this r Betelgeuse over r sun quantity squared, we can just plug in the number 1180 for that. For the temperature, we actually need to plug in the real temperature. But the point is that when we do that, we say, Betelgeuse, as a consequence of this method, has a luminosity of 188,000 solar luminosities. So Betelgeuse is almost 200,000 times as bright as our sun. I mean, the main reason that Betelgeuse appears so bright in the night sky is because it actually is a really bright star. And of course, if you wanted to, you can convert that to watts, but in this case, we were really interested in seeing how it compared with our sun. How about R136A1? R136A1 is a lot smaller than Betelgeuse, but it's much hotter in surface temperature. And the fact that it's so much hotter is what really makes the difference. Remember, luminosity goes as temperature to the fourth power. So it's still a lot bigger than our sun, but 35 solar radii instead of 1180. And so that gets squared, but that temperature ratio gets taken to the fourth power. So R136A1 is 8.7 million times as luminous as our sun. It's actually the most massive star known, over 300 solar masses, and the brightest star that we know of as well. Here's an artist's rendition of this thing. And later in the course, I'll actually show you a picture of the cluster in which it lies. Now, recalling that as you shift to higher temperatures, the wavelength of peak luminosity shifts toward shorter wavelengths, that actually means that if you know the mathematical function for blackbody radiation curve, then you could find the place where the slope of that function is equal to 0. So using calculus terminology, take the derivative and set it equal to 0. When you do that, unfortunately, you get a transcendental equation, which means you have to solve it numerically. But upon solving it numerically, we get a formula for the wavelength at which a blackbody would be expected to have its peak radiation as a function of temperature. So you tell me the temperature of the blackbody, I'll tell you the wavelength at which you have the highest intensity. Okay, so let's try this out. It's about 2.9 million kelvins divided by temperature, nanometers. So how about for the sun? Well, plug in the sun's temperature into that equation, and cancel the kelvins, and we get the peak wavelength in nanometers of 502 nanometers. Not surprisingly, that's right smack in the middle of the visible part of the spectrum. After all, that's kind of why our eyes evolved like that. What about Sigma Orionis, which is the bright star that actually is ionizing everything around the Horsehead Nebula in that nice picture that I showed you a little while ago? Well, Sigma Orionis has a surface temperature of 32,000 kelvins. Well, how does that plug into this equation? So you have 2.9 million kelvins divided by 32,000 kelvins times nanometers for that peak wavelength. And when you plug in that temperature, you get a peak wavelength of 91 nanometers. 91 nanometers. Well, guess what? 91 nanometers is energetic enough, 91 nanometer photons are energetic enough that they will ionize a hydrogen atom. And that's exactly what this star Sigma Orionis is doing. It's ionizing all of the hydrogen in the area around here, and as those electrons and the hydrogen recombine and cascade down energy levels, we'll talk about that in the next video, they end up emitting light of particular wavelengths. In particular, with a wavelength of 656 nanometers, which is probably the most common wavelength in the visible part of the spectrum in the universe. And as a result, combined with the other wavelengths that it emits, I believe at like 478 nanometers, around 435 nanometers, that combination of wavelengths gives you this nice pinkish glow that you often see in star-forming regions. Indeed, Sigma Orionis is a young star that just formed a few million years ago. Indeed, this star and stars like it are really what are responsible for causing the nice pinkish glow that you often see in star-forming regions. Now, another cute little way of writing Wien's displacement law is recalling what we got when we plugged the surface temperature of our sun in and got a peak wavelength of 502 nanometers. Well, 5,777 kelvins, which I think is what we actually plugged in, or maybe we did plug in 5,770, but that is pretty close to 5,800 kelvins, and 502 nanometers is pretty close to 500 nanometers. So how about we just round those and keep those in and say, okay, well, we say that lambda max times the temperature is equal to 500 kelvins, or sorry, 500 nanometers times 5,800 kelvins. This is a convenient approximation because a lot of times, if you happen to know the temperature of a star or something like that, then you can just plug it into this equation and perform some mental math to figure out the peak wavelength. But here's the thing, guess what? Astronomers don't do it this way. They don't know the peak temperature of stars and use that to figure out the peak wavelength of the blackbody spectrum. Instead, they measure the spectrum of the star and they note where the peak wavelength is, and based on the wavelength at which you have the peak intensity, they plug that into the equation and use that to figure out the temperature of the star. So we measure wavelengths of peak intensity. We use those in Wien's displacement law to figure out the temperature of the blackbody. So that's how it's done. So again, this just gives us, doing it this way, gives us a shortcut. You could do it the same way in the regular formula. The fact that the peak wavelength is equal to 2.898 million kelvins divided by the temperature in kelvins times nanometers, or just do the approximate method of taking the result that we got by using that formula with the sun. But either way, again, what astronomers typically do is they measure the intensity, the wavelength of peak intensity, and plug that into Wien's displacement law. In fact, you can even get a better chance of doing some mental math by rounding 5,800 kelvins up to 6,000 kelvins, and that works out relatively well. So if you have a relatively hot star that has a peak wavelength of 300 nanometers, or an intensity at peak intensity at a wavelength of 300 nanometers, then plugging that into the equation, you realize, okay, 300 nanometers, so divide both sides by 300 nanometers, that's 500 divided by 300, that's 5/3, times roughly 6,000 kelvins would end up giving you 10,000 kelvins, or using the 5,800 Kelvin approximation, a more precise estimate of the temperature of 9,700 kelvins. So, long story short, that is how astronomers figure out temperatures of stars and temperatures of other objects that are good emitters and good absorbers of radiation. Now, what about objects that are not? For objects that are not, that's where we need to examine spectral lines. And even objects that have noticeable spectral lines, in a lot of cases they actually do make reasonably good blackbodies. But here's the thing. Objects that have spectral lines give us a lot more information about their composition and other characteristics, and it's that we will examine in the next video. Thank you for watching, and I'll see you then.